and said in 2 hours I can definitely cover some algebra. So let's get to it. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. I just pray you be with us. Help us to just have clarity of thought and just to accomplish what we need to today, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right, so if you look at my course notes for this, and I'm trying not to just follow those. I'm really trying to find a new narrative for this material, which is hopefully more interesting. And I thought, I'm still convinced that Rentlen has a better path than my notes. But you guys don't have a copy of Rentlen, so that's a problem. I'm not sure if my wife will support me buying each of you a copy of it. I don't know. I might, though. I don't know. I'm on the cusp. Anyway, so in my notes, though, you'll notice I talk about coordinate change at the end of the chapter. That's wise. I shouldn't lead with coordinate change. That's crazy. That's the worst possible presentation. I have showed you the worst conceivably, that is the worst thing to do at the start because it's the most confusing thing, I think. So anyway, let's get back on track here. So let's talk about tensors and multilinear maps, and so those will be the same. So we'll start with V, vector space. I'm going to think of it as the span of E1, E2, En. So this is a vector space. Over either R or C, right? And then we can talk about the dual space to V. Right, the dual space to V is what it happens to be the span of E upper 1, E upper 2, E upper n, where E upper j acting on E lower I is by definition Kronecker delta ji for all ij. Now that's a derived result. This is the so-called dual space, right? Now I guess technically speaking that's not basic. What's the basic thing is that the dual space is what? It's the set of linear maps from V to the field that you're looking at. So more descriptively, it's the F homomorphisms from V to F, where F could be R or C. In finite dimensions, if V is finite dimensional, right, then V and V dual are isomorphic. All right. Let's see here. Let me give you an example of a couple of these. For example, if V is equal to Rn, then if you look at phi of x1, xn, if that's equal to x upper j, right? Well, this defines phi an element of V dual. So, for example, the coordinate maps are, in some sense, well, in this sense, they're elements of the dual space. They're covectors. You can prove that this mapping phi is linear, right? You could define it in terms of the dot product, right? Phi of x is equal to what? It's equal to x dot ej. Now you see right there, and here I'm using ej as the standard basis, obviously, but so here you see a sort of a violation of our index note, our index convention, the up-down index convention, right? Well, I guess that's also true of this, right? So, I mean, this contravariant covariant thing I was talking about last class, we can, sometimes we can't quite get it to work on definitions especially. All right, anyway, let me give you a more interesting example. Example 2, if x is an element of the vector space, right, and x is equal to x1 e1 plus xn en, then if you take any vector, let's say row vector a1, a2, an, and I'll keep it real here for just a second, 1 by n, right? This gives a particular dual vector defined as follows. Phi of x is equal to a1 x1 plus a2 x2 plus plus a sub n x upper n. So of course, if you take v equals to Rn here, you see why people might say that there's some sort of unique correspondence between, say, row vectors and the dual space in this sense, right? I mean, this could be rewritten as what? If let's just suppose v is equal to Rn for a second here. This is a1 an times x1 xn, like that, right? So you could think of this as basically phi is the dual vector which is associated to the row vector a1 through an. So it's a pretty common thing if you listen to people who know more about these things. They'll think of the dual space as being row vectors if the vector space is column vectors. But I wouldn't get too carried away with that. All right. Example 3. If v is the set of continuous functions from 0 to 1, then you can define phi of f equal to the integral from 0 to 1 of f of t dt. This is a linear functional. Now, the term linear functional tends to be used more in the context of functional analysis, where things get a little bit more interesting there. In the case of functional analysis, you're dealing with infinite dimensional vector spaces, and it's no longer the case that v and the dual have to be the same size. In fact, they're usually not. I mean, oftentimes the set of linear functions over an infinite dimensional vector space can be way, way huger. Is that a word? No. Sorry, too much Trump. Anyway, so that's an example of a linear functional. You can see that it's linear in f, right? And the output's a number. So that's a mapping from continuous functions to real. So that's a covector. Example 4. If there exists a base, if beta is a basis for v, all right, so if beta is a basis for v, and if we can choose v an element of the basis, then there exists a unique linear functional let's say little v star, an element of v dual, such that what? V dual acting on v gives us 1, and v dual acting on w gives us 0 for all w in the basis with the vector v removed. That's true both in finite and infinite dimensions. Now, if you want to read more about infinite dimensional vector spaces and duals, I recommend Curtis' little linear algebra book, Abstract Linear Algebra. That's where I got these examples. As you recall, that's where the unfortunate masterpiece problem with the systematic typo came from. But don't give up on that book. That book has great insight into more abstract questions in linear algebra. In fact, I found the thing Dr. Skambordis was talking about, which is the theorem he was quoting was that if you have an infinite dimensional vector space, you can pick any vector in there. And there is some basis for the vector space where that vector is in it. That's the theorem that requires Zorn's lemma in fancy math. In infinite dimensions, that's hard to, well, it's not hard, it's just technical. Okay, so now that we have a little bit more examples of dual vectors, I just wanted to give you a few examples rather than just saying it abstractly. Now I'm going to go back to more abstract things. So if you take the dual, you could take the dual again, right? You could talk about the double dual. You say double dual? Yes, double dual. What's the double dual? It's V dual dual. V double dual is the dual of the dual. Like so. So what this would be is what? It would be F, a mapping from what? From V dual to the scalars, such that what? You can replace this with the reals if you want, if that's helpful to you. But it could be the reals or the complexes. Such that what? Such that F is linear, right? Linear map from V dual to F. In other words, I could have just said that this is L of, sorry. So it's really L of V in this notation. Or it's the hamana F with F. Yeah. Okay, now there's actually an isomorphism of the dual and the double dual as follows. So if you give me, here's the mapping, we'll call it psi. Psi is a mapping from V to V double dual. How do we define it? Here's the mapping. We say psi of V is equal to V hat. Put a hat on it. Now how does that work? Where V hat, now if I'm saying V hat's in the double dual, right? So I have to tell you how V hat works on a linear functional or a covector alpha. So what would that be? Definition here. So the answer is pretty much the only thing it can be, which is that it's alpha of V. Now that makes sense because now I have, right, this is for all alpha in the dual. So that is a number because alpha is a dual vector, right? So the dual vector acting on the vector gives me back a number, and this shows me how I can produce a number from the double dual vector acting on the dual vector. So to be more obnoxious about this, the specific definition is psi of V of alpha of X is equal to, what is it? I think I've made a mess now. Why did I do that? I already have given you the definition. Why am I making it worse? Is this clear? I mean, do you want me to try to express it again in different symbols? Do you understand, Nathan?
I think so.
Joe? You're here?
We'll get there.
We'll get there. Okay, I'll accept that. Now, what this really does, though, is this gives us a way. So basically, the idea is that V maps to V hat. So this is basically what I would say is a passive object. It really doesn't. If you tell me the vector is going to act on something, I'd be like, "What are you talking about? It's a vector. It just sits there, right? It's a point in a set. Why would it act on something?" On the flip side, this v hat, which is naturally associated to v by this rule here, well, this is something active, right? So a double dual vector, it acts, or it eats dual vectors, right? It eats covectors and spits back numbers. We use this in the construction of formulas. All right? Yeah.
What's above that equal sign? The v hat alpha equals alpha v.
Oh, this definition. This is really the definition of v hat. Yeah. All right. So we're talking about psi of v should be an element of what? V double dual, right? So how do you define something in here? You have to define it by how it acts on what? Element of the dual space. And so that is alpha of v. So there's the isomorphism expressed without the hat. But the hat is useful for our thinking. Right? So you can prove, in fact, that that's an isomorphism. Right? The proof is on page 43 of Curtis. Not that you have it, but it's there. I mean, it's pretty easy to see that the kernel of this is what? What's the kernel of psi? First of all, is it linear? Is psi a linear map? Is it linear in V? If I take V1 plus V2, I get alpha of V1 plus V2, which is alpha V1 plus alpha V2. Right? So then, since that holds for all alpha, it gives me that psi of V1 plus psi of V1 plus V2 is psi of V1 plus psi of V2, and I can pull scalars out much the same. So it's definitely it's giving you a linear map on covectors, and then to prove it's an isomorphism, you just need to show it's injective, right? So show the only if psi of v is 0, if it's the zero double dual vector, it must be that v itself was 0. So for this to be the double dual vector that's 0, it must be that it sends all covectors to 0, right? But you notice we have an example 4. If beta is a basis for v, then there exists a unique linear functional such that the covector takes v and spits back 1, right? So that's there. There's an alpha there which is non-zero on v. In the space of all covectors, there's that one covector, at least, that gives you back something non-zero when you feed it v. So the only way that this can be 0 for all covectors is if it's the zero map, and that proves injective. Maybe I'll try to give you guys surjective in a homework. I'll try to set it up so that it's not hard. Now this is called a natural isomorphism of the vector space in its double dual, because this has there's no coordinates here anywhere. It's all just maps, right? There's no basis dependence. The isomorphism between the v and its dual is based on the choice of the basis beta, which I haven't named yet, right? So I'm calling this beta. I'm calling this the dual basis, beta dual, right? And so the isomorphism here basically is given by pick a basis. Here's the dual basis. You prove that they're both bases, and then you count. Dimension is n. Dimension is n. They're isomorphic. Right? From the viewpoint of category theory, that's not a natural isomorphism. All right. However, if we change the category a little bit, if we don't say that this is just a vector space, if we say this is a vector space paired with what's called an inner product or I think I'd like to call it a pseudo-inner product. If we have that, then there is a natural mapping independent of basis in terms of what's called the metric. Or perhaps I should say pseudo-metric. All right, so I'll talk about that a little bit later, but what I want to get back to is how to build tensors from the basis and the dual basis, all right? So, are we good? So what is a tensor? What was our, let's just remind ourselves, what was the definition? The tensor of type what? Type P, Q would be what? Multilinear maps. Multilinear maps from where? Now, one of these needs a dual. We're talking about real valued tensors. By the way, you could talk about other thing valued tensors. We just work with real valued tensors because it's our starting point. But multilinear maps from the appropriate number of Cartesian copies of the dual and the vector space. Now, I'm trying to remember the notation. That was the index structure, right? So if T is an element of this thing, then T is equal to, maybe I should make this like I think I make this like a curvy T, just so we don't, I never use this as a symbol for an element of the space. So just to give the space a different look than its elements, let's say that that's the space of tensors. And really, to be clear, it's over V. But sometimes I don't write the V dependence because the context is clear. In fact, most of what we're going to do, V is just Rn. All right, so I'm being more abstract than I need to be perhaps, but it actually makes it more conceptually clear if we're a little bit more abstract, believe it or not. So T is equal to something like a sum I1, I2, all the way out to IP, J1, all the way out to JQ, and the components where the I's and the P goes upstairs, right? So I1, IP, and then J1. And I guess, well, I don't know. I haven't decided. I usually try not to write them over each other because the reason you don't, you're like, why don't you just write these over here, right? The reason is, as we go on, there becomes ways to raise and lower these indices, so you need to keep track of, there's just one slot. There's P plus Q slots here, and they're either up or down in the index notation. Does that make sense? There's a what?
There's an order.
Yeah, there's an order to them, exactly. Think of there being as like I said, there's P plus Q boxes here, and we'll learn that if V is a metric space, or rather if V is a vector space with an inner product, pseudo inner product. It bothers me to call them inner products because inner products, when I think inner product, I think positive definite. But some people say inner product, they actually allow for other things than just positive definite, so whatever. Anyway, the language is miserable here. Different books say different things. But there's those P plus Q slots. All right. So, and then what? Well, EI1 tensor, EI2 tensor, tensor, EIP tensor, E upper J1 tensor, tensor, E upper JQ. This is what a arbitrary element of this is a type PQ tensor, right? By the way, if you wanted to make this thing not real valued, instead of making these components real numbers, just make them something else. Now that I have this, we can clean this up, right? This is acting on, what do the first P things act on? how about the last Q things? These are dual vectors, right? These are definitely on V. These are vectors. They act on the dual. Now, when I write that, what am I thinking about? I'm thinking about the double dual, actually, right? I'm thinking of these actually as being double dual vectors because those naturally act on V dual. And these are the so-called components of T. With respect to the given basis. And by the way, you can, I'm gonna flesh this out in examples, but this truth is ubiquitous. It's everywhere. You get these simply from taking T and evaluating on the appropriate basis and dual basis vectors. I mean, we'd kind of like to prove this. All right, so I think I proved it in the case of type 2-0 mappings last time, right? Like I went through this calculation that showed you a bilinear map could be written as a sum of the, like E upper I tensor E upper J, and the components were given by B acting on E lower I lower J. Was there a question? Yeah.
In the original definition on that line, we have cross I equals 1 to B.
Oh, well, this is the p-fold Cartesian product. So if I were to write it out in gory detail, that's just a shorthand for this p-fold times.
So they're all cross products.
The p-fold Cartesian product of V with itself. V dual with itself, excuse me. Yeah. Okay, so let me just kind of work from the base up. So like V, you have things like a typical basis element is what? It's E lower I. What's V dual? What's a typical basis element? E upper J, right? Now, this is what? This is type 0-1. Notice that if I have a typical thing, something like alpha, but rather V, is equal to a sum I equals 1 to N, V upper I, E lower I, then this would be naturally associated with what? A mapping from what to what from... Oh, you know what? Let's not... I could do this, but this is stupid. Let me stop that. Let me stop it. I have more interesting things to get to today. Let me not do that. So this is in V dual. What's something in so by the way, as I described last time, this set of things is what? It's interchangeable with what? What did we say? It's interchangeable with good grief. The p-fold tensor product of V dual tensored with the q-fold product of V, right? Oh, other way around. So like a type, type 0-2 tensor, something is what? It's like B from what? From V cross V to the reals. And yes. Thank you. So this one would be what? Type 0-1, right? So type 0, 2 is something like this. And we proved last time that you can write B as a sum over I and j of B I j, E upper I tensor E upper j, right? And so it makes sense to say that this is an element of V dual tensor V dual as well, right? Because it's built from tensor products of dual basis elements. See that? But it's a map on V cross phi to R. So I guess, I mean, technically speaking, I didn't give you some important definitions that I really should. They're not very exciting, but they should be made. So, for example, what's the definition of E, let's see here, E, let me just do, let me be Machiavellian in this definition, all right? EI1 tensor, tensor EIP, tensor EJ1, tensor, sorry, lots of tensors, EJQ. This acts on what? Right, we need P dual vectors and Q vectors. So let's say alpha 1. I don't know. I have to number them. It's annoying, but okay. Alpha 1. These are not components, right? These are actually dual vectors. Alpha 1 alpha P, and then vectors. Let's say V1 VQ. When I label things, I almost always just put the labels downstairs. These are not components. They're just labels. So I have, these are elements of V dual, and these are elements of V, right? And what's the definition? Well, the definition of this tensor acting on this is simply alpha 1 acts on EI1. All the way out, product, all the way to alpha P acts on EI sub P. And really, I mean, if you want me to be kind of more honest, what's going on here is that we have EI1 hat acting on alpha 1, right? That's the concept where that's coming from. Is in some sense you're really identifying the vector space with its double dual to make this definition. You see that? But from another perspective, what else could you write? I mean, we need some formula that's linear in these entries, in each entry, right? And it's a number. So how do you get a number from alpha 1 and E1? Well, you let the covector act on the vector. That's all you can do. And then likewise, these dual vectors just act on the vectors. So like EJ1, V1, EJQ, VQ. Yeah.
Are those on the right side of the equal sign, those commas that we have?
These are commas. Oh, I mean, you said the right-hand side, didn't you?
The right-hand side.
You said right-hand side, didn't you? Sorry.
Are those submitted by commas as well?
Right. Let's see here. These are dots, like multiplications.
Oh, those
Yeah, multiplication. Now, my big claim is that if you take the set of all such tensor products of basis elements and dual basis elements, those give you a basis for the type PQ tensors over V. In other words, my claim is that you can prove that these, if you take the set of all possible ones, they're linearly independent and they span the space. Now, I showed you that explicitly for the type 0,2 tensor last time. You really don't want me to try to prove it in general in class, right? That would be not terribly enlightening and kind of an annoying thing to see. Sounds like a great homework problem, doesn't it? I'm just kidding. That would be mean. Oh, well, no,
I want to see it in class.
Just because you don't want to see it in class doesn't mean it has to be a homework problem. Fair enough, yeah. Okay, so, all right. Now I think with that, I feel like we have at least settled the basics better. Now there are special kinds of tensors, which are, so I mean, let me actually write in words what I just said. So here's the theorem that the tensor space of tensors of type PQ over V is equal to a span of, you know, let's say EI1 tensor EIP, tensor EJ1 tensor EJQ. Where you should understand that if I write this I1 in IP and J1 and JQ, all the indices are allowed to take all possible values from 1 to n. So, and let's call this thing, I don't know, what do you want to call this, beta PQ or something? I don't know. I don't have a good notation for it. And beta PQ is a basis. So in other words, the dimension of the type PQ tensors over V is what? P times Q times the dimension of V. Wait a minute, is that it even? I'm not sure about that. I don't think that's right either. In fact, the answer is this. No, still wrong. Plus Q. Well, tell you what, I'm going to say that. Let's go on. We'll see if we agree with me as we go on or if we need to fix this. I think it's right, though. A very special kind of type 0. Now, there's a very special kind of type 0,2 tensor I should talk to you about, which is called a metric. Well, perhaps pseudo-metric. Or pseudo-inner product maybe would be better. I don't know. It's like it's
appropriate though.
it's like a pseudo spelling of pseudo. So it's double. It's like the double dual, but for. So I'm just going to call it metric though, because I hate saying pseudo. It's a useless word that's really not well, but. Anyway, words. Now, on V. So what we have is G from V cross V to the reals, or, well, let's say to F. So that's F is either equal to the reals or C. That this is going to be called a metric. What do you need? There's a couple conditions you need. One, G is bilinear. Two, oh, not bilinear, sorry. G is sesquilinear. Yeah, sesquilinear. You know, I don't know.
That's the definition of F, is that it's either the reals or the complexes.
Yeah, either F is either reals or complexes for us. You can safely replace it with a subfield of the complexes, but pretty much we're thinking either real or complex, honestly. Our time is limited in here. I'm going to forget about C for now. we'll come back and do C when we feel like it. I don't think it really matters much to us today. This can be defined for a complex. Then, if you do it for a complex, then sesquilinear is what you have. Sesquilinear is like 1.5 times linear. You have linear in one slot, and you have conjugate linear in the other. I'll make a homework problem. Susquehanna. Yeah, I grew up on the shores of the Susquehanna. Well, not Susquehanna, but okay. So let's keep it real. Then a metric on a real vector space is a bilinear map. Which is symmetric. And 3G is non-degenerate. Now, so what is, now bilinear, we could say this in our current lingo, this just means G is an element of what? It's a type what? It's a type 0-2 map, right? It's a type 0-2 tensor that says it's bilinear. Now it's symmetric, that's something new. What does symmetric mean? That means G of xy is equal to G of yx for all x and y in V. That's symmetric. Non-degenerate, what's that mean? Non-degenerate means that if G of xy is equal to 0 for all y in V, that implies what? If the metric of x and y, or if you want, you could say the inner product of x and y is 0 for all y, it must be that x is what? 0. Yeah, that's non-degeneracy. Now, we can write G as follows, right? G of xy is equal to, what is it equal to? It's equal to a sum, by the calculation I went through last time. I'll tell you what, I'll go through it again. So this is what? G of sum over I of x upper I, e lower I, sum over j, y upper j, e lower j, right? Bilinearity allows me to pull out the sum over I and j and the components x sub I, y sub j, and I'm left with what? G, ei, ej. Now, of course, I can rewrite this as a sum over ij of gij, e upper I tensor e upper j, all acting on x, y. Because again, a type 0-2 tensor is something in V dual tensor V dual. It's the sum of the tensor product of dual vectors with themselves. Now, so there's a matrix here, right? So you can look at the matrix of G, which is what? The matrix of these components. And you can think about that matrix. What are the properties of this matrix? So let's call this, Rentland just calls it big G for the matrix of the metric. So this matrix of the metric, so bilinearity basically gets recaptured as you can write, now these things I'm assuming are n in what I write here, okay? But if we're on Rn, and we can work with the standard basis, then g of xy is just what? It's just x transpose G, Y. Now here, I'm assuming V is Rn, so I don't have to work through a coordinate map. Otherwise, I'd have to filter this through a coordinate map. Symmetric is what? Yeah, that works out that G transpose equals to G. Non-degenerate, what's that mean? Basically, that's telling you that X transpose GY is equal to 0 for all Y implies that X is equal to 0, right? So through a little bit of standard linear algebra, that means that G inverse exists. Or that the determinant of G is non-zero. Now there's, yeah. Where? Oh, this right here? Those are commas. Sad commas, but commas nonetheless, yes. Now here's a theorem for you, and I'm gonna walk you through a proof of this theorem in your homework, I hope. And in fact, it's not hard given that we've already proved the spectral theorem. See, because it's a symmetric real matrix, right? So you know that it has an orthonormal eigenbasis. But so if let's say V1 well, how to say this? There exists a G orthonormal basis for V. In other words, beta V1 Vn such that G of Vi Vj is equal to plus or minus Kronecker delta Ij for all Ij. Two vectors are said to be G orthogonal if the metric of those vectors is 0. They're unit vectors if the metric on them if the metric on the vector with itself is either plus or minus 1. We have to allow for minus 1 too because we're not assuming that the metric is positive definite here. So it's not a metric in the sense that we have more carefully defined in other courses, which is why I probably should say pseudo-metric. Okay. Are we good? This is known as Sylvester's theorem. It says that basically any metric, there's a system of coordinates where the metric can be written as a sum of squares minus a sum of other squares. So the most important examples, of course, just Rn with dot product, right? So G of xy is equal to x dot y. That's an example, right? And the other example that I like, now this is actually, if you want to associate Rn paired with G, you can call it En. So this is Euclidean n space. Euclidean n space is Rn paired with the usual dot product, the usual inner product. You can look at the transformations which leave the dot product fixed, the so-called orthogonal transformations, right? What are those? Well, they're just orthogonal transformations. They're literally rotations and reflections, right? Now, if the other example that we deal with in here is Rn with so-called Minkowski product. The Minkowski product is something like this. If I have G of xy, it's minus x naught y, x upper naught, y upper naught, plus the sum I equals 1 to n minus 1 of x upper I, y upper I. So the matrix here looks like zeros. So Rn paired with this metric is known as Minkowski space. So the notation for that is if you have Rn paired with this Minkowski metric, you can just say it's so-called Mn, Minkowski space. Now that's the geometry that underlies special relativity. The zeroth component's like time direction, the other components are like space direction, so you have space-time. And the geometry of space-time is not that of Euclidean space, it's that of Minkowski space. And so the transformations which leave the metric fixed, right? If you look at linear transformations that do this, all right, transformations which leave the metric fixed between arbitrary points, those are known as Lorentz transformations. If you look at the set of all of them, they form a group. Anyway, I will craft some homework problems that let you think a little bit more about these. They're really, it's very easy stuff. It's not really not that complicated. If it may be new to you guys, but the linear algebra of it's very, very simple and very beautiful. All right, now there is one other example of a metric. The reason I'm talking about metric in here, I mean, yeah, I do have some physical examples I want to do later. I want to actually look at electromagnetism built over space-time, so I need to know a little bit about this, all right? But the other reason is that I want to talk about the Hodge duality, right? And so Hodge duality is built over a concept of a metric on the space of all wedge products of vector spaces, let's say. So what is a wedge product is, I guess, is the question. So these symmetric, right? You can look at the space of symmetric tensors. The metric is an example of a symmetric tensor, right? What? Yeah, I'll leave that. It's easy in two entries. There's symmetric and there's anti-symmetric. So to talk about symmetric or anti-symmetric, I really need all of the entries to either be vector spaces or all to be dual spaces. So let's just, for clarity, let's suppose that T is an element of the tensors. Let's just look at the ones that act on vectors. That's kind of the most natural thing. So that's what, type 0p over v, right? So what's that mean? T is a mapping from what? From p copies of v to the reals, right? So 1, T is symmetric, right? If T of, let's say, V1, Vp is equal to T of V I1, Vip. Maybe I should be more explicit here. Let me say sigma of 1, V sigma of P, where sigma is a mapping from the set, well, how to say this? Yeah, it's a mapping from NP to NP, which is a bijection. This is a name in math, the bijections on the set of elements from 1 to p. What are these called?
Permutations.
Permutations, that's right. So this makes sigma an element of the permutations on 1, 2, p, all right? So basically, it's symmetric. What that means is you can shuffle the inputs however you like. The output's the same. That's complete symmetry of the tensor. What's complete anti-symmetry? If whenever we swap any pair of inputs, a minus sign is generated. So in other words, t of like v1 dot 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 vj dot 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 vk dot 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 vp is equal to minus t of v1 dot 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 vk dot 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 vj dot 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 vp, like that. And that's true for arbitrary pairs. You generate minuses. See what I did? I just swapped this and this over here. You get a minus. If that's true for all possible pairs, it's called antisymmetric. In terms of combinatorics, though, that's equivalent to saying that t of v1 dot dot vp is equal to the sine of sigma times t of v sigma 1 v sigma n, p, rather p. Or sine is equal to plus or minus 1, depending on whether the permutation can be written as an odd number of transpositions or an even number of transpositions. We've proven group theory, any permutation can be written as a product of cycles of length 2, in other words, transpositions. And the number of transpositions it takes to express a permutation is uniquely even or odd, although it's not unique. But anyway, I don't want to get into like the group theory of permutations here, so goodness gracious, I really like the thing I wrote in black for people who haven't had group theory. But the thing I wrote in purple, it makes you happy if you know group theory. Yeah. All right? Both of these give you special subspaces of the tensor space of type, type, man, this language, it just, what is this? This is type 0p, right? Okay, so if you look at this space of all possible tensors of type 0p, there's this privileged class. There's the so-called symmetric tensors, the so-called anti-symmetric tensors. What happens if you add two symmetric tensors? Guess what? You get another symmetric tensor. Because you can work it out. Likewise, if you add two anti-symmetric tensors, you get another anti-symmetric tensor. So these form subspaces of the set of all possible tensors of type 0p. All right? Now, fact, if you look at the tensors at type 0,2 over v, it's equal to the symmetric type 0,2 over v tensors, direct sum with the antisymmetric, the type 0,2 over v tensors.
What's the usage again? In the first part you wrote in purple.
That is, the sine of sigma is either equal to 1 or minus 1 if sigma is a even permutation, and if sigma is an odd permutation.
What exactly does that mean?
Ask me after class. It's group theory. It's somewhat technical. I mean, it's not that hard really, but it's, again, I mean, it means that sigma can be written as an even number of what are called transpositions. This one can be written as an odd number of what are called transpositions. Transpositions are permutations which just flip one thing, one pair.